everyone, and welcome to lecture 25. Today we are going to talk about optimal choice and a very quick recap as to where we are so far in consumer choice. So there are two foundations on which we are developing this theory. One is the notion of consumer preferences, which tells us how a consumer ranks or orders various consumption bundles. And the second is about consumer budget, which talks about affordability, right? So we started the discussion by talking about preferences, how a consumer is ordering or ranking various consumption bundles. We listed the three axioms or structures on preferences, if you prefer: completeness, transitivity, and more is better. This allowed us to talk about utility functions, which was a mathematical representation. And what this utility function did was it assigned a particular number which denoted the level of happiness or satisfaction associated with different consumption bundles. Then we said we could pictorially represent utility levels by drawing indifference curves. So we had talked about indifference curves, which is essentially the set of all consumption bundles which give the consumer the same level of utility. And the key, or sort of the main takeaway from this discussion on consumer preferences leading to indifference curves, was the slope of the indifference curve, which we defined as the marginal rate of substitution. And recall that the marginal rate of substitution is a statement of your preferences, of a consumer's preferences, and it tells us the amount of good Y that a consumer is willing to give up to get one more unit of good X, right? And we said that based on the utility function, we can derive the marginal rate of substitution at a particular point on the indifference curve by simply computing the slope dy dx. And we derived dy dx, and the expression for MRS was minus mux by muy. So, and the units in which MRS was measured is units of y upon units of x. So this was about the MRS part. On the other side, we talked about consumer budget, which is, well, given that the consumer has some amount of income, there are only some subsets of good X and good Y that the consumer can afford. So budget constraint talks about affordability, and the budget constraint essentially tells us that if Px is the per unit price of good X, Py is the per unit price of good Y, and the income of the consumer is given by the income I, then the budget constraint is Px times X plus Py times Y is less than or equal to Y. I mean, in simple words, it essentially says your expenditure has to be less than or equal to the income. And one important takeaway from the analysis of the budget constraint was deriving the slope of the budget line. So we wrote it as Y is equal to I divided by Py minus Px by Py times X. Okay. So all of this has been completed. So before we do optimal choice, my suggestion is you should go back and review this material before we talk about optimal choice. So let's proceed, and I want to talk about the optimal choice of the consumer, of the representative consumer. So what do we mean? So by optimal choice, essentially the problem that we are trying to solve is the following. So consumer's problem is to maximize her utility, right? Recall, the utility function is a function of the amount of good X and the amount of good Y that she consumes. The consumer is interested in choosing the amount of good X and the amount of good Y to maximize her utility. But now this is a constraint problem subject to expenditure being less than or equal to the income, right? So the consumer wants to maximize her utility subject to the budget constraint. Okay. Now what we'll do is, before we solve the problem mathematically, let's understand the problem by drawing a picture. Let's find out what the optimal choice is, and then we will take a particular example and find out what the optimal X star and what the optimal Y star are. Okay. So to that end, let me first draw the budget line and an indifference curve. So this is xy, and then on the side, let me just put the expressions for mux and muy. Recall, mux is delta u delta x, muy is delta u delta y, and the slope of and the budget line is given by y equals I divided by py minus px upon py times x. So y is equal to I divided by py minus px upon py times x. So let's get the budget line. So if I spend all my income on good y and do not buy good x at all, the maximum quantity of good y that the consumer can buy is I divided by py. On the other hand, if the consumer spends all her income on good x, the maximum quantity of good x that she can buy is I divided by px. And as before, this is my budget line. This is my budget line. And everything inside this triangular zone is my budget set. Now let me take an indifference curve which is given as follows. So suppose the consumers, so let's say I have an indifference curve which is given by IC1. So the indifference curve is telling me the utility level, and let's say the utility level is given by IC1. This is going to be some number based on the utility function. Okay. Now you give me the specific functional form. I know what the coordinates of this point are. Let me call this point to be point A. Let me call this to be point A, right. So at this point A, the consumer is consuming some amount of good x and some amount of good y. Okay. So suppose, so let's make a note of it. Suppose the consumer is at A. Now there are two things that I want you to notice about the point A. The point A is on the budget line, right? Because it's on the budget line, it's going to satisfy the budget constraint. So this bundle A is affordable. Okay, so A is affordable as it is on the budget line, right? So I'm only talking about bundles which are affordable. I could have taken something inside the budget set also, which would strictly satisfy the constraint. Expenditure is strictly less than income, but I have chosen to take a point on the budget line, and you will see why in just a moment. The other thing that we note here is that A is also on the indifference curve, right? It's on the indifference curve IC1, right? So since it's on the indifference curve and on the budget line, I want to compare the slope of the indifference curve at A, and I want to compare that with the slope of the budget line. Okay, so the interest for us is we want to compare the MRS at A. Let's say I want to compute the absolute value of MRS at A, which is going to be the slope of the indifference curve at A, right? Because recall, MRS is nothing but the slope of the indifference curve, the amount of good y that the consumer is willing to give up to get one more unit of good x. I want to compare the slope with the slope of the budget line, with the slope of the budget line. I'll write BL to denote the budget line. Okay. Now, if you look at the picture, well, what would be the slope of the indifference curve at A? Well, the slope of the indifference curve at A could be obtained by drawing a tangent to the indifference curve at A, right? So if I were to draw a tangent to the indifference curve at A, I'll be able to get the slope. Let me just draw it again. So this would be the tangent to the indifference curve at A, right? And I'm taking the absolute value of this slope, and I want to compare the slope of the indifference curve at A with the slope of the budget line at A. Now clearly you can see that if I compare the two things, the absolute value of the slope of the indifference curve, if I take the absolute value, that's going to give me a larger number than the slope of the budget line. So the absolute value of MRS at A is going to be greater than the absolute value of the slope of the budget line. Recall, the slope of the budget line is always minus px by py. So that's minus px by py, irrespective of whether it's at A or any other point on the line is going to have a constant slope. So I can rewrite this as minus mux upon muy at A being greater than the absolute value of minus px by py. Now because I'm taking the absolute value, I can essentially drop the minus sign, and I can write this as mux by muy at A is greater than Px by Py. I'm going to drop the subscript A because the context now is very clear, correct? So I've compared the slopes, those are negative numbers by definition. I've taken the absolute value and I've written it as Mux by Muy is greater than Px by Py. Let's do one more step of algebraic manipulation, and since everything here is positive, so I'll bring the Px down here, so I can write it as Mux over Px is greater than Muy upon Py, which then implies that Mux upon Px minus Muy upon Py is strictly greater than 0. So keep this in mind. So what did we learn? When we compared the slope of the indifference curve at A with the slope of the budget line, it turns out that the absolute value of MRS is greater than Px upon Py, and this algebraic manipulation is going to give me Mux upon Px minus Muy by Py is greater than 0. On the other hand, since the point A is on the budget line, so suppose that the consumer is currently spending, so let's say the income of the consumer is rupees 100, I'm just making an imaginary number, and then this 100 is split between good X and good Y, right? So suppose he is spending rupees 60 on good Y and he is spending rupees 40 on good X, right? So I could have found out what the quantity of XA the consumer is consuming at A, the quantity of Y that consumer is consuming at point A, multiplied by those prices adds up to 100, but it turns out that Px times XA is equal to 40 and Py times Ya turns out to be equal to 60. So let's suppose that the consumer is currently splitting his budget at the point A in this particular format, right? So 40 and 60 are just some numbers that I have thrown which add up to 100. This could very well have been 30 and 70, 25 and 75, 50 and 50 also, it doesn't matter, okay. Now I want to do the following experiment. So suppose I reduce the expenditure on good Y by rupee 1, right? So currently I am spending 60 rupees on good Y. I am decreasing the expenditure on good Y by 1 rupee. So essentially now I am taking away 1 rupee of expenses that I was currently incurring on good Y. Okay. Why am I doing that? You will see in just a moment. So we have reduced expenditure on good Y by rupee 1. Now if I have reduced expenditure on good Y by rupee 1 and each unit of good Y costs me Py rupees, right? So recall Px and Py are the per unit prices. So Px and Py are the per unit prices. So if I spend Py rupees, I will get one unit of good Y. So if I have only 1 rupee, I will not get the entire good Y, I will get 1 upon Pyth unit of the entire good. So because I have reduced my expenditure by rupee 1, it implies that it reduces amount of good Y, it reduces the amount of good Y by 1 upon Py units, right? Think of Py being 10 rupees, right? So each unit of good Y costs 10 rupees. So you give 10 rupees to the shopkeeper, he gives you 1 unit of good Y. If you give him 1 rupee, he gives you 1/10 of the entire unit of good Y. So in general, if you pay Py rupees, you get 1 unit of good Y. So if you spend 1 rupee, you are only going to get 1 upon Pyth unit of the entire amount. But now you have reduced your expenditure on good Y by 1 rupee. So the amount of good Y that you are buying has gone down by 1 upon Py units. Now because the amount of good Y has gone down by 1 upon Py units, the delta Y essentially is 1 upon Py. Now keeping the amount of good X the same, if you decrease your expenditure on good Y by 1 rupee, you are going to get some amount less of good Y. That's going to decrease your utility, right? So you are going to come to a lower point, and how much of the utility is going to decrease can be obtained by the MUY. So this reduction in the amount of good by 1 rupee, so let me also write it here, MUY is delta U upon delta Y. So essentially the change in utility due to 1 upon Py units less of good y is equal to MUy times delta y, right. So the change in utility delta u would essentially be MUy times delta y, and I know that my delta y is 1 upon Py units, so I can essentially say this is MUy times 1 upon Py, so this is MUy by Py, okay. So just to sort of reiterate what I have done, I am trying to identify if I reduce my expenditure on good y by 1 rupee, that's going to give me some amount less of good y, but notice I am keeping the amount of good x the same, that is reduced the amount of good y. Essentially I will be on a lower indifference curve, which is the same as saying that my utility has actually decreased. So this is going to be a negative, this is going to be, since delta y is a negative number, this is going to be a negative number, but I am right now just going to write it as a change in utility. The signs will adjust in my final step, okay. Now what am I going to do with this 1 rupee that I decreased? I am going to transfer this 1 rupee onto good x, right. So instead of spending 40 rupees on good x, I am now going to spend 41 rupees on good x. Previously I was spending 40, now it is 41. I am spending 60 previously on good y, now it is 59. Notice this also adds up to 100. So I am not violating any budget constraint. So I took away 1 rupee from good y and I am going to transfer the rupee 1 onto good x, right. So it's as if I have 1 rupee more to spend on good x. I will also put MUx equals delta u upon delta x here, so that we are going to make use of it. Now if I have 1 rupee more to spend on good x, then the amount of good x that I can get is going to be higher. So previously I was at A, we came down to some point, and now I am able to buy some more amount of good x, and I am exhausting all my budget, right. So I am going to come to a new point on this budget line A prime. So I transfer the rupee 1 onto good x, which means that I can buy 1 upon Px amount, have 1 upon x Px amount more of good x, right. Think of each unit of good x costs you 5 rupees. You spend 5 rupees, you get an entire unit of good x. But if you spend 1 rupee, you are going to get 1 upon 5 units of good x. In our world, good x and good y are divisible in any amount that we want. So that gives me an additional amount of good x, which implies that keeping the amount of good y at whatever that level was, if I spend 1 more rupee on good x, my utility again is going to change. So my change in utility due to delta x equals 1 upon Px amount more of good x is going to be equal to Mux times delta x, and the delta x is 1 upon Px. I can simply write it as Mux upon Px. So on one hand, my utility due to having 1 rupee less on good y decreased by this amount. On the other hand, my utility due to spending that 1 rupee on good x increased by this amount, which then implies that my net change in utility is going to be Mux upon Px minus Muy upon Py, right. So after we did this shift of 1 rupee by decreasing the amount spent on good y by 1 rupee and transferring it to good x, there was a net change in utility, and I know that this net change in utility is given by this expression. And I know that at the point A, notice these are very small changes that I am doing. So for these very small changes, I know that Mux upon Px minus Muy by Py is greater than 0. So I know that this is greater than 0. So what we have shown is, if the consumer was initially at the point A, I could do this experiment of decreasing expenditure on Y by 1 rupee, transferring that on to good X, and take the consumer to a new point A prime, and at this point A prime, the consumer is going to be at a higher level of utility. So he has moved to IC2, which is at a higher level. So let's call this to be A prime, right? He has moved to a new point which is at a higher level of utility. So clearly A cannot be the optimal bundle, right? So the consumer's utility implies consumer's utility has increased, implies A cannot be the optimal, bundle, right? Because what have we done? We have shown that without violating the budget constraint, I can take away 1 rupee from good Y, transfer it on to good X, and make the consumer better off, in the sense that the consumer now gets a higher level of utility and his happiness level has increased at A prime. Now, does that mean that A prime is my optimal point? Well, again we can do this experiment, that we decrease the expenditure on good Y by 1 rupee, transfer it on to good X. I will again find out what the MRS at A prime is. I will compare it with the slope of the budget line. You will notice that the MRS at A prime also is greater than the absolute value of MRS at A prime is also greater than the absolute value of the slope, and therefore I can always again do this reshuffle by transferring 1 rupee from Y onto good X. So I keep on doing this change, right? So I was at A, I keep on doing this change. Where will I stop? I will eventually stop when I can no longer do this reshuffle and make the consumer better off. And that's going to happen when the indifference curve, is tangential to the budget line at the point, let me call this to be B. So I keep on doing this change till I reach the point B. So keep the transfer from good Y on to good X and stop when the absolute value of MRS is equal to the absolute value of the slope of the budget line, which occurs at the point B. Because if I were to compute the MRS at B, that would be drawing the tangent, and the budget line itself is the tangent to the MRS at the point B. So this tells me that in plain English, this tells me that the slope of the indifference curve at B is equal to the slope of the budget line, right? And if I take the absolute values, I can essentially make the same statement. These are equivalent statements. Now mathematically, let's write it. What this implies is that MUX upon MUY, right? MUX upon MUY is equal to PX upon PY, which is the same as saying that, so recall MRS is minus MUX by MUY, but I am actually taking the absolute value. So I have MUX upon MUY. On the right hand side, the slope of the budget line is minus PX upon PY. So I am taking again the absolute value. So the minus signs get dropped. So I can claim that the optimality must satisfy this condition. This is called the tangency condition of optimality. This is the tangency condition of optimality. So there are two things that pictorially we can see. One is that the optimal bundle is on the budget line, and not just that, at the optimal bundle, the slope of the indifference curve in absolute terms and the slope of the budget line are equal. So let's also make a note that the optimal bundle is at B, and the optimal bundle satisfies the tangency condition. Right? So I can start from any point A, do this reshuffle and reach the point B. Now as an exercise, I will ask you to repeat this if instead of starting from A, suppose the consumer, I take some other point D here, right? So at the point D, the consumer has some amount of XD and some amount of YD, right? Is D the optimal bundle? Well, I can again do the similar analysis like I did at the point A, but now I will need to take away 1 rupee from good X and transfer it onto good Y. So I suggest that you write down the same set of arguments, and to help you get started, let me just give you a hint. What you need to do is you want to compare the slope of the indifference curve at D, which is the absolute value of the slope of this indifference curve at D, with the slope of the budget line. You will find that the absolute value of MRS at D is less than the absolute value of the slope of the budget line, right? And that should tell you in which direction you ought to move, right? Whether you should transfer 1 rupee from Y or whether you should transfer 1 rupee from X. Okay, but I will leave that for you to write down. So just write down the same set of arguments like how I have written here, so that you understand this better. Okay. Now let me show you an example on how you can use the tangency condition. So suppose my utility function is X times Y, and I am given that the income of the consumer is rupees 800. The price Px is rupees 20 per unit. The price of good Y is rupees 40 per unit, right? Now, what is my objective? My objective is to find the optimal X and the optimal Y. So let's first write down the budget constraint. My budget constraint, so essentially what are we solving for? The optimal X and the optimal Y. So I'm solving for two unknowns. If I'm solving for two unknowns, I need two conditions. Well, one is going to be my budget constraint, right? Because my optimal bundle is on the budget line. So it must satisfy the equation on the budget line. So 20 times X is my expenditure on good X. 40 times Y is my expenditure on good Y, must equal 800, right? I don't need to write less than equal to, because I've already seen that my optimal bundle is on the budget line. This I can rewrite as, so if I divide by 20, I can write it as X plus 2Y equals 40, right? So this is my one condition. So if I were to plot this line, so at Y is equals to 0, X is equals to 40, and at X equal to 0, Y is 20. So this is my budget line. I also know that my indifference curve is tangent to the budget line, right? So what else do I know? I also know that at the point B, the absolute value of the slope of the indifference curve is equal to the absolute value of the slope of the budget line. So I can just write this as MUX upon MUY is PX upon PY, and PX upon PY is nothing but 1/2. Now we already know that MUX is del U del X, which based on this expression del X of X times Y is simply Y, and MUY is del U del Y, which is the derivative of X times Y with respect to Y is simply X. So this gives me MUX upon MUY, which is Y upon X, is PX upon PY, which is 1/2, which tells me X equals 2Y. So notice there are only two conditions, the budget line as well as the tangency condition. So I can plug in X equals to 2Y in equation 1, which will give me 4 times Y is equal to 40, which gives me Y star equals 10. So my X star is equals to 20. So on the graph, this is my X star equals 20, this is Y star equals 10, and this is my optimal bundle. What we will do next is, I will show you one more example where if my utility function is of a slightly different form and we use the same tangency condition, we will see that it may not work. Okay, we will see that example, and after that we will look at a few applications of consumer choice. We will do that in our next lecture. Thank you.